Right, so I know that a lot of students struggle a little bit with phase difference, so I wanted to talk a little bit about phase difference and just look at an example or two. Also, a lot of students have a hard time with the wave graphs and interpreting them and getting data from them, and so I wanted to look at one of those as well. So that's what's going to happen in this last video, all right? So the first one here about phase difference, we're going to calculate the phase difference between two displacement time graphs shown in the figure below. It's figure 9. I didn't label it, but it's figure 9. Give your answers in seconds, radians, and degrees. All right, so looking at the wave, right, we can tell, well, I guess we should probably double check, make sure these are actually the same wave. You can see that it goes from 2 seconds down to negative 2 seconds, and that's the case for both of these. So we can see that, 2 down to negative 2. We can see, let's see, this one has a period starting at 0, and the period takes 2 seconds, right? It goes from the top down to the bottom, back to the top again. That takes 2 seconds. If I find the top here, it's right after that first line, right after 0.2 seconds. So I go top down to the bottom and top again, and notice here's the 2 seconds, and it's just after that first line. So it looks like it's about the same there. So I think we're pretty confident saying that these two are basically the same. So let's find out what the phase difference is, right? So this one is at 0, and then this one, the maximum here, is right there. Okay. Now, we are reading it off a graph, which means there is some estimation involved, some guessing. It doesn't, you can tell the marks. Let's see, there's 1, 2, 3, 4, 5 marks between 0 and 1. So each one of those marks is going to be 0.2 seconds. It doesn't look like it's right on the line. It looks like it's a little bit afterwards, but it doesn't look like it's right in the middle either. So I don't think it's 0.3. So I'm going to go ahead and say that this is about 0.25 seconds. So letter A is going to be 0.25, and that is the phase difference, 0.25 seconds. All right, now I need to give it in radians or degrees. Okay, and you can do it however you want. Some people are more comfortable working with degrees, some are more comfortable working with radians. I'll go ahead and do degrees first because I think that's how a lot of you will do it. Okay, recognizing that the whole curve, right, is one full cycle, right? So one full cycle is 360 degrees, okay? Now, the whole cycle was 2 seconds, and we're off by 0.25 seconds. Oh, blast. Okay, 0.25 seconds. So because of that, then we want 0.25 out of those 2 seconds. And so that should be pretty straightforward calculation. Go ahead, punch it into your calculator. We go 0.25 divided by 2, and then we multiply it by 360. And so I got about 45 degrees. So letter B, 45 degrees. Okay. From there, you can then turn that into radians. Some of you will know already that 45 degrees is about pi over 4. If you don't, then remember to get from degrees to radians, you just multiply by pi over 180. And if you multiply by pi over 180, then you should get 0.25 pi. I like to just leave the pi the way it is, so 45 over 180 is 0.25 or 1/4. The way that's usually written is pi over 4. So that means that the graph here on the right has advanced or has a positive phase difference of 0.25 seconds or 45 degrees or pi over 4. All right, so that's the basic idea for how a phase difference question would work. All right, let's look at another question. Graph 1 below shows the variation with time t of the displacement of a traveling wave. Graph 2 shows the variation with distance x along the same wave of its displacement d. So we've got a graph that's putting, graph 1 has a specific graph with respect to time and its displacement, and then graph 2 is with respect to displacement. Okay, now the interesting thing about this is that we have two different graphs representing the same wave, okay, but they're different things, right? Graph 1 is showing what happens over time, right? So it's showing specifically a point and what happens to that point over time. That point has a positive displacement, that point has a negative displacement. So this isn't actually showing the whole wave, it's showing an individual point along that wave. Okay? Now this one down here shows what the displacement looks like over a specific distance. So this is what I see on the string. If my string was 2.4 centimeters long, then this is the wave that I would see with it. This is more of like a snapshot, okay, at one particular point in time. All right, so this one shows me what's happening as time progresses. This one is a picture of what it looks like right now. So for the given wave, find amplitude, wavelength, frequency, and speed. So that's what we're hopefully going to do right now. Okay, so the first thing is amplitude. Now amplitude I should be able to get from both of those graphs, right? The first graph I can see the amplitude of an individual point is 4 millimeters. And I can see the graph down here, I get the same thing, right? That wave has an amplitude of 4 millimeters, which makes sense because for this wave, if a particle moves 4 millimeters, that means that the wave as a whole should have a maximum displacement of 4 millimeters, right? The wave can't be any bigger or smaller than its individual pieces, their motion, okay? Next, we've got wavelength. Okay, so for the wavelength, I'm going to look at the bottom picture. Now, the reason is because this picture up here shows me what the particle is doing over time, but it doesn't show me how long the wave is. Okay, but the one down below, because it's a snapshot, it gives me a very good idea of how long the wave is, right? I can see that at this moment in time, it has a length, that wave going from the middle to the top to the bottom, from to the crest to the trough and back to the middle again, it has a total length of 2.4 centimeters. So the wavelength is 2.4 centimeters. Okay, so I'm getting that from the snapshot because that's something that I can see. That's what the string would actually look like right now. Okay, the next one asks for frequency. So frequency is how long does it take to go from one point until it gets back to that same point again. Okay, so distance isn't really going to help me there. I need some time. So in this one, I'm going to look at the first graph because the first graph has to do with time. And I can look at a single particle and I can say, well, that particle starts here and then it goes down and then it comes back up again. And it looks like it starts around, each one of those is a tenth. So that one right there is 5, 6, 7, probably about 0.075, right? Each one is 0.01 because 0.01, yeah, 0.01. And then it gets back here again, right here, which looks like it's about right there, which would be looks like about 375. And so when I subtract those to get the total amount of time that it took to do it, then I get a time or a period of 0.3 seconds, right? You can do that with any point on the graph. I chose this maximum, but if you feel like a different one, a different point, or maybe these right here along the equilibrium, any of those will work. Just make sure that if you choose points along the equilibrium, do not choose adjacent places where it crosses, right? Because it hasn't finished a whole cycle then yet. It does need to go through a whole cycle. Now, I did only get period. I need to finish that up by getting the frequency, but I know that frequency equals 1 over period, and so I can do that by just doing 1 divided by 0.3, and I get 3.3 repeating hertz, okay, or seconds to the -1. Either one of those is fine. You can use whichever one. Make sure that you're comfortable with both because obviously they can give information in either one of those forms. Okay. Last question is about the speed, and we know, of course, that the speed comes from the wavelength times the frequency, or the frequency times the wavelength. That's in a formula packet. So if I do that, I do need to put them, I guess I can leave it. The wavelength is in 2.4 centimeters. The frequency is in 3.3 hertz. So I put those together. Notice that I use centimeters and hertz. So if I go 3.3333 times 2.4, then I should get 8. And so the velocity equals 8 centimeters per second. Now, that's really neat because I couldn't have gotten that information from one of these graphs individually. But together, knowing something about the time and the motion, and also knowing something about the displacement and what it looks like in a specific instant, I was able to put those ideas together to get the answer. All right? Last one. This has multi-parts, but this is our last question. Okay? With reference to the direction of energy transfer through a medium, distinguish between a transverse wave and a longitudinal wave. All right, so this one, this is a question that we've answered many, many times already, but it's so important because you do have to be able to distinguish between the two and be able to think about them with reference to specific situations. Really all it is a transverse wave means that it asks us with reference to direction of energy transfer through a medium, distinguish. Okay, so for a transverse wave, if the energy is flowing this way, then the motion of the medium, the particles, they're perpendicular. For transverse. Right, and remember that just means that as the wave travels this way, as the wave's moving, that means individual particles are moving up and moving down with the wave, right? Longitudinal is where if the energy is transferring this way, then the motion of the particles is parallel. Okay, that's all that matters, is that longitudinal means that the motion of the particles is parallel, the transverse is perpendicular. All right, let's look at another situation. The graph, same situation, new question. The graph shows the variation with time of the displacement of a particular water particle as surface water wave travels through it. Determine the wave's frequency and amplitude. Okay, so after our last example, that should be pretty straightforward, pretty easy to do. Sorry, I don't know why all that stuff keeps showing up. We'll get rid of it right here. So the amplitude, of course, is just how tall that wave is from its equilibrium. So we'll go ahead and get that right here. So from the center, it goes up like that. And it looks like it has an amplitude of 8 millimeters. Okay, pretty straightforward. You'll notice that if I had done it on the bottom, that's also 8 millimeters. And then the frequency, I'm just going to use the period. I'm going to use the easiest way that I can think of right now, which is to start at 0 because it does look like it's going through 0, 0 there. I'm going to go up, down, and then back to the middle. So again, it looks like, wow, each one of these little lines is not 0.01 because I've got 10 of them between 1 and 1.5, so each one is 0.005. Okay, so it's 0.05 from one to the next, and so divide that by 10, each one is 0.005. So I count off 1, 2, 3, 4, 5, 6, looks like about 7. And so that would mean 0.035. And so that means that the amount of time it would take would be 0.135, right? Which is less than 0.15, and it's more than 0.1, so that makes sense. Recognize that the middle here would be 0.125 if you're having a hard time picking those pieces off, but that would be my period. Again, you're reading off a graph. They'll be a little bit flexible, but you do need to be within reason, pretty close. Okay, and then of course frequency equals 1 over the period. So I'm going to do 1 over 0.135, and I get a frequency of 7.41 hertz, or seconds to the -1. All right, so let's move on to the next part of the question. Okay, keep that information because you are going to need it in just a minute, at least some of it. Okay, So the next question, if the speed of the wave is 12 centimeters a second, then calculate the wavelength of the wave. All right, well, that should be pretty easy because we know that velocity equals wavelength times frequency. You'd be surprised, or maybe you shouldn't be surprised by now, how often this equation comes up. So we're going 12, notice that this is in centimeters per second, okay, equals wavelength times the frequency. So frequency from the previous slide was 7.41. That was rounded, but that should be close enough. When you are doing it on your calculator, you want to keep all those digits, okay? I didn't memorize all those digits when I went to the next slide, but you should have those on your calculator. And so you want to use actually all of the digits in your calculation to make sure that you're as close as you possibly can be. All right, so now I'm going to just divide both sides by 7.41, and I get 1.62. And because this was in centimeters per second and this was in per second, then when I divide those, I'm left with centimeters. So 1.62 centimeters is the wavelength. All right. Next, I'm going to get a little bit harder here. Okay, this graph shows the displacement. I'm going to write down what we had before, that the frequency was 7.41 hertz, and our wavelength was 1.62 centimeters, and the velocity was 12 centimeters per second, just because we may need it. This graph shows the displacement of a particle at position x equals 0. So now it's changed. It's now talking about the displacement of a single particle. Okay. Sketch a graph showing the variation with distance along the water surface of the displacement of the water surface at t equals 0.20 seconds. Okay. So now it wants, instead of, this is the graph that we had before with respect to time, we want to create a graph now that's with respect to what the graph as a whole would look like, okay? So this actually isn't all too difficult. They don't want too much. It's just a sketch, but we do need to include the important pieces, right? So they do want variation with distance, so we're going to have x centimeters. Okay, because that's the distance. Remember, the wavelength was in centimeters, so that's what we're going to have. And then variation with distance along the water surface of the displacement of the water surface. So so the displacement is this, the d, right? That's your amplitude there. So we already know that the wave has an amplitude or maximum displacement of 8. So it's going to go up to 8, and it's going to go down to -8. And then we know that the wavelength is 1.62 centimeters. So the wave will have a wavelength of 1.62. So I'm actually going to mark this right here as 1.62 centimeters. So I just need to make sure that between here and there, I complete a full wavelength. Now, the question is, where does that wave start? Well, if we look at the original graph, we see that this point right here is starting at 0, 0. So that means at the beginning, at time, well, we want to look at time 0.2. So time 0.2 would, let's see, let's look at this guy right here. 0.2 would be this point in time right here. Okay, so I see that this particle, the particle which I'm going to put at the very beginning here, that particle has a displacement of 0. So I know I'm going to start at 0, 0. Now from there, it looks like the particle is going to go down. So what do I need to make my graph look like so that as my wave moves to the right, the particle will go down? So I've got two choices, right? My graph can either go up like this, or it can go down like that. Okay? Now, if I'm saying that the wave moves in this direction, which of those two waves is going to make my particle move down as time progresses? Well, some of you will see it right away. Others may need to draw what the wave would look like in the next second. Okay? So, if I take my blue graph there and I show what it would look like in the next second, if that graph moved a little bit to the right, then it would look like this, right? It would move a little bit to the right, and it would look just like that. What happened to my point? It moved down. It had a negative displacement, just like is shown in this graph, right? Because it is showing the particle at position x equals 0. That's this guy right here. That's why I put it at the beginning. Okay, now just to show what would happen if you had chosen the other graph, okay, let me get rid of this. Let's look at the green graph. What would have happened if I had taken the green graph and moved it a little bit to the right? So if I move this, that means that it should be here. Okay, and so now you can see that the green graph has moved a little bit to the right. Okay, but what happened to this point? You see how it's moved up? That's not what we want. At 0.2 seconds, we want the motion of the particle to be downwards, which means the blue graph was the correct one, and so my final answer should be this, where it goes from 8 to -8, and then it goes all the way up to that wavelength, which was, I think, 1.62, right? So this is in centimeters, this one is in millimeters. All right, so that's that part. All right, so here's the last part of the question. The wave reaches an underwater shelf such that the wave fronts have an angle of 30 degrees with the shelf. After reaching the boundary, the wave travels at 18 centimeters a second. Determine the angle between the direction of the new wave and the shelf. All right, so let's see if we can first draw a picture of what's going on here, because I am at a loss. So here's my shelf. It says that the wave fronts are coming in with an angle of 30 degrees with the shelf. So here's my wave coming in. Here's my wave fronts. Okay, so something like this. It says that that is 30 degrees. Okay, now that's all nice and good, but remember, so actually what it's asking is, so the wave comes in and then it changes speed. It's actually going to be going faster when it gets through, all right? Now, before we do anything, remember that most of the time when we talked about speeds changing, we weren't talking about the wavefront, we were talking about the ray. And so what I would like for us to do is first, before we show what it looks like on the other side and do any calculations, let's look at the ray. So the ray should be coming in like this, right? So this is the direction of the ray, the direction of the wave, right? So the ray comes in, the ray is perpendicular to the wave fronts, it's going to come through. Now, if I draw in the perpendicular, right, the normal, so remember if it's going faster, it should bend away from the normal. And so it's coming in like this, but it's actually going to bend away and go a little bit faster like that. Okay, so now I need to go through and figure out what all these dang angles are, right? So originally it was 30, so this was 30 degrees right here. Okay, now if I look at the right angle here, that means that this has to be 60, right? And then I also know that the ray and the wave front, so if I look at the ray and the wave front right here, that should be 90 because those are perpendicular, which means that this should be 30 degrees, right? So I've got a picture now of the ray coming in 30 degrees to the normal, and then it's leaving, hopefully, with a larger angle because now it's going faster, okay? Now, in order to answer the final question, we have to use Snell's law. This is just a situation with refraction, okay? So Snell's law says that sine of theta 2 over sine of theta 1 equals velocity 2 over velocity 1. So we should be able to throw all those numbers in, right? We are looking for the new angle, so that's this. We've got sine of theta 1, so that would be sine of 30 because that's the angle at which it's hitting, right? And then we've got the original speed, which was 12, right? So the 12 was the original, 18 is the new one, and so we should be able to go ahead and do that math. The sine of 30 is 1/2, You can check that on your calculator. You can do your right-hand triangle, whatever you need to do. So I'm going to multiply both sides by 1/2, which is going to give me sine of theta 2 equals, if I bring the 1/2 over, that's going to give me an 18/24 now. And then I'm going to do the inverse sine of both sides, or you could probably do some type of insolve, I think. The calculator I'm working with right now on my computer doesn't have that ability, so I am going to do an inverse sine right here. And I get 48.5 degrees. So theta 2 equals 48.5 degrees, which is larger than the original one, just like I had hoped. And it gives me the angle between the direction of the new wave and the shelf, because the direction is represented by the ray, not by the wavefront. Okay, so there you go. We got our answer. That's the end of that question, and that's the end of the video.